Hi, this is Tzvi Rosen. Welcome to another lecture on matrix theory. This time we'll be talking about linear independence and bases. To kind of communicate why bases are important, we're going to start by trying to list all of the vectors in R2. Okay, you'll recall R2 can be defined as the set of pairs x, y, where both x and y are real numbers. Okay, so to list the elements here, well, we remember that the 0 vector is important, so let's put that in there. And then let's try to list a few more. We could do 1, 0, but I know that I'm supposed to be able to scale these. So I should be able to multiply it by 2, by 3, by 4. I can also scale it by negative numbers, be able to get -1, -2, 0, -3, 0. So this was just using the first coordinate, but I could also get some numbers in the second coordinate. So I could take 0, 1. I could scale that by 2 or 3 and 4, etc. Okay, and I haven't even tried using rational numbers smaller than 1 or real numbers that are not rational. And throughout this whole thing, I'm only using vectors where one of the coordinates is 0. So we could add these together. You know, we could get 1 pi minus 2 half, etc. So it should become pretty clear pretty quickly that this is going to be a fool's errand. We're not going to be able to list all of the vectors in R2. But we want to be able to describe all the vectors in R2. So instead, we're going to list ingredients for R2, and then we'll say how to combine them to make all of the vectors in R2. So our ingredients will be the vectors 1, 0 and 0, 1. You'll remember these as the standard basis elements. These are E1 and E2. Okay? And to get any vector in R2, to make any vector in R2, take A and B, real numbers, and set V to be the vector that you're trying to generate. Just set it be equal to A times E1 plus B times E2. Now, any vector I'm interested in, it should be easy to see what those A and B will be. So for instance, the vector 0, 0, this corresponds to 0 times E1 plus 0 times E2. On the other hand, the vector 1 pi, that's 1 times E1 plus pi times E2. So we've replaced the infinitely many elements of this list of a vector space with just 2 ingredients, and then directions on how to combine those ingredients to get all of the vectors in the space. Okay, so that's going to be our agenda for the rest of the lecture, is how to assemble these ingredients list in a reasonable way. So the first thing we want to be aware of is that the ingredients shouldn't be redundant. For instance, if you have, kind of using the metaphor of a ingredients list, so if you have a bottle of garlic powder on your shelf and salt, and you also have garlic salt, which is just garlic powder and salt, it's going to get confusing because the two of these together are just going to be the same as this. And so there will be no way for somebody who's writing a recipe to know whether they should use the garlic powder and salt or the garlic salt, because it's the same thing. Okay, so these sets of ingredients will get confused. Okay, in the same way, if we have ingredients like 1, 0 and 0, 1, but we also have an ingredient that looks like 1, 1, those are going to get confused because I could just take the two of these, add them together, and I would get the thing on the right. So I'm going to try to avoid this. Okay, so avoid this redundancy by defining linear independence. Okay, let's define that on the next slide. So we're going to take a set of vectors v1 through vn be a set of vectors in a vector space V. Okay. And let's call this set S to be abbreviated. So we say that S is linearly dependent if some vector vi in your list can be written as a linear combination of the other vectors in the list. Okay, and an example of what this might look like is if you have 4 vectors and v3 is equal to v1 plus 2v2 minus 1/2 v4. Okay, so v3 can be written in terms of the other vectors, so the set would not be linearly dependent in that case. Linearly independent in that case, it would be linearly dependent. Okay, so on the other hand, if S is not linearly dependent, then we say it's linearly independent. Okay, just pretty reasonable definition. Okay. So something that you can figure out pretty quickly is that instead of trying to look at your list of vectors and figure out if one of them can be written in terms of the other ones, it's enough to find a non-trivial formula for 0. Okay, so when we say 0 here, we mean the 0 vector. So first, let's note what a trivial formula for 0 is. That means that you take the 0 vector as the linear combination of your v1 through vn by just setting the coefficients all to 0. 0 times v1 plus 0 times v2, etc., up to 0 times vn. Okay, so the first statement I'm going to show is that if some vi can be written in terms of the vj that are not equal to I, then 0 has a non-trivial expression. Okay, and the way we would get that, so if we have vj equals, some collection of, let's write it this way, c1 v1 plus etc. plus up to cj minus 1 vj minus 1 plus. Okay, now we're saying that vj is not part of this formula, so we'll skip right to cj plus 1, vj plus 1 up to cn vn. Okay, well then 0, and we know that this has an unspoken coefficient of 1 here. So if I subtract 1 Vj on both sides of this equation, then I have the 0 vector here is equal to C1 V1 plus up to Cj minus 1 Vj minus 1 minus 1 Vj plus Cj plus 1 Vj plus 1, etc., plus up to Cn Vn. So I took this alternative formulation of Vj and I turned that into a non-trivial expression which is equal to 0. Okay, and I know this is non-trivial because at the very least this coefficient is non-zero, right? We know that coefficient is minus 1. So this is a non-trivial expression equal to 0, which we derive from this failure to be linearly independent, or this success in being linearly dependent, I guess. Okay, if on the other hand 0 has a non-trivial formula, then some vi can be written in terms of the other vectors. So what does that mean? Well, if we have 0 equals, C1 V1 plus up to Cn Vn non-trivial, then that means that one of these Ci's is non-zero. Right? Otherwise, it's trivial. Okay, but then that means I can multiply the whole thing by 1 over Ci, or minus 1 over Ci, that's probably better. Minus 1 over Ci, so we get C1 over Ci V1, etc., minus 1 times Ci, minus Cn over Ci, sorry, minus 1 Vi, should be. And then this is Vn. And that gives us, by adding Vi to both sides, Vi equals minus C1 over Ci V1, etc., combined with everything that's left on the other side of the equation. Okay? So what we've shown here is that having an expression for one of the vectors in terms of the other vectors is the same as having a non-trivial expression for 0. So that's what we can always look for. Instead of trying to piece together which vector you can write in terms of the other ones, always just look for a non-trivial expression for 0. So to show dependence, find C1 through Cn not all equal to 0, such that C1 V1 plus up to Cn Vn is equal to the 0 vector. On the other hand, to show independence, the way that you do that is start out by supposing C1 V1 plus up to Cn Vn equals 0, and then deduce that C1 through Cn must all be 0. Okay, show that if C1 V1 plus up to Cn Vn equals 0, then C1 must be equal to Cn, which is 0. So all of these coefficients have to be equal to 0. In other words, there's no non-trivial formulation for 0. All of the coefficients have to be 0 if you're getting 0. Okay. So let's try and apply that in practice. We'll start with some vectors in R2. Let's look at the vectors 1, 0, and 0, 1. This was our ingredient list from earlier. Now we're curious, are these independent or dependent? So looking back, if we wanted to show they're dependent, we want to combine them in a non-trivial way to find 0. If we want to show it's independent, we want to show that any non-trivial combination, or rather any combination which is equal to 0, must be trivial. Okay, so I'm going to assert that it's going to be linearly independent based on the fact that these are the standard basis vectors, as you might remember. So let's see what happens when we take C1, 0, 1, 0 plus C2, 0, 1 and set this equal to 0. Well, the 0 vector, this is just the vector whose coordinates are both 0. So what this means is that C1, 0 plus 0 C2 must be equal to 0, 0. But I can combine these two vectors in the usual way, and I'll get C1, C2 equals 0, 0. But these two vectors can only be equal if all of their coefficients are equal. So that means all of their coordinates are equal. So that means C1 equals 0 and C2 equals 0. And what that proves for us is that our set of vectors must be linearly independent. Okay, because again, we started with an arbitrary linear combination which gives you 0, and we deduced, using logical reasoning, that both of those coefficients had to be 0 in the first place. Okay, on the other hand, this set of vectors, I believe, is dependent. Okay, and we're going to prove it by taking C1, 1, 0 plus C2, 0, 1 plus C3, 1, 1. This should be equal to 0, 0. And in order to prove that this is dependent, we need to find C1, C2, and C3 that are not all 0, which satisfy this equation. So putting this all together, what this would mean is that C1 plus C3 in the first coordinate and C2 plus C3 are equal to 0, 0. And this is not bad, because if we set C3 to be minus 1, then C1 and C2, we can set them both to be 1, and this equation is satisfied. Okay? So that implies that the set is linearly dependent. Okay. Now let's look at some vectors in R4. Okay, here we have 3 vectors, each with 4 coordinates, and we're curious, is this dependent or independent? So we're going to set up this equation as before, C1, 1, 2, minus 1, 0, plus C2, 0, 1, minus 2, minus 1, plus C3 is equal to the 0 vector. Okay. One way to solve this is actually using an augmented matrix. So we can take 1, 2, minus 1, 0, 0, 1, minus 2, minus 1, 1, 1, 1, 1, 0, 0, 0, 0. And we can use row reduction to come up with some constraints on our C values. Okay, so let's go ahead and row reduce. We'll take minus 2 row 1 plus row 2 and then row 1 plus row 2. And down here, we won't touch it for now. So we get 1, 0, 1, 0, 0, 1, minus 1, 0, 0, minus 2, 2, 0, 0, minus 1, 1, 0. Okay, you might already sense where this is heading. But if we take this second row and we add 2 times the second row to the third, and just 1 copy to the fourth row, what we get is 1, 0, 1, 0, 0, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so what this tells us is that C1 plus C3 is 0, and C2 minus C3 is 0. Okay, so this isn't hard. We can take C3 to be a free variable. Let's fix it to be 1. And then C2 will also be 1, and C1 will be minus 1. Okay. And so as a result of this computation, because we have minus 1 times v1 plus 1 times v2 plus 1 times v3, and that's equal to the 0 vector, this implies the vectors are linearly dependent. Okay. Now let's consider polynomials in P2. This is the space of polynomials of degree at most 2. Okay, and it's not hard to figure out that this is a vector space. You can always add polynomials together. You can multiply them by scalars. So this is a vector space, and arbitrary elements in that vector space look like ax squared plus bx plus c. Okay, so let's consider the set at the left here, 1, x plus 1, and x squared minus 1. Is this a linearly dependent set or an independent set? Okay, dependent, independent. Okay, well, let's figure it out. If we have c1 times 1 plus c2 times x plus 1 plus c3 times x squared minus 1 equals the 0 polynomial, well, I can figure this out in steps. I know that the only quadratic term, the only x squared, is in the last vector here, the last polynomial. So the fact that there's no quadratic term, so because right-hand side has no x squared, that means that C3 has to be equal to 0. Okay? Because that's the only place, there's no other place where you can cancel the x squared. Okay, but if C3 is equal to 0, then the only place with an x term is the second vector. Okay, and so similarly, so right-hand side has no x, so the C2 equals 0. And then finally, C1 times 1 equals 0 implies that C1 equals 0. So we started out with a linear combination giving us 0. And we deduced that all of the coefficients were 0, so that implies that the set is linearly independent. Okay, and we will temporarily, let's see how we can do this. Okay, we're going to ignore the presence of that example. And now we're going to do that example on this page. So we will ignore the first example this time. Oops. So now we want to show that we want to determine whether x plus 1, x minus 1 is linearly independent or linearly dependent in this space. So we have C1, we're going to consider C1x plus C2x plus 1 plus C3x minus 1 equals 0, and we're going to see if we can find a non-trivial solution or if all of the solutions are trivial. Well, straight away, I'm seeing that I can combine like terms, and what I get is C1 plus C2 plus C3x plus C2 minus C3 is equal to 0. So to make sure that the constant term is equal to 0, I just take C2 equal to C3. And then to make sure that the first term is 0, I just need C1 to be equal to minus C2 minus C3. So if for example, I decide to set this to 1, then this would just be equal to minus 2. Okay? So I can take minus 2 times x plus 1 times x plus 1 plus 1 times x minus 1, and I'll get 0. So that tells me that this set is linearly dependent. Okay. Now taking a bit more of a general example, suppose you have v1 through vr, and you're in a space Rn. Okay, so that's where you have n coordinates, but you have more vectors than the number of coordinates you have. Okay, well then we could use the following reasoning. When we take c1 v1 plus up to cr vr, we're saying this is equal to 0. This is going to be a system of n equations in R greater than n variables. Okay, so there will always be a solution. Okay, this implies that a solution always exists. Okay, and in particular, a non-trivial solution always exists. Okay, so I should be able to find real numbers, not all 0, C1 through CR, that satisfy this equation. So that means that the vectors, a set of vectors of this size, will always be linearly dependent. So looking back a bit, we had up here an example with 3 vectors in R2. We could have just observed, hey, this is 3 vectors, but we're in R2, so since 3 is bigger than 2, we can be sure that this is dependent. Okay, so hopefully you've got a feeling now for what linearly dependent and linearly independent mean. And now we're going to get back to our ingredients analogy and figure out the right way to write our ingredients list. And that ingredients list is going to be called a basis. So if we have a set of vectors S equal to v1 through vn, and it's a set of vectors in a finite dimensional vector space V, and we're going to put that in parentheses because we haven't defined dimension, but let's just think about it as Rn for some integer n. Then S is called a basis for V if first S spans V, and second, S is linearly independent. So the second one we've just discussed at length. And let's recall the first one, S spans V, means that any vector V in V can be written as a linear combination of elements in S. Okay? So everything that you want, everything that you're looking at in V can be written as a linear combination of our ingredients list in S. Okay? And that's what it means to be a basis. First part, you can actually cook every recipe you'll ever need to cook. Second part, there's no redundancy. So you don't have ingredients that really do the same thing, like garlic and garlic powder and salt and garlic salt. Okay. So how do we show that something is or is not a basis? So to show it is a basis, you want to show that it spans. And show that it's linearly independent. On the other hand, to show it's not a basis, show that it does not span, i.e., there's some vector that you can never construct using these. Not expressible as a linear combination of S, or alternatively, show it's linearly dependent. Okay, so as is always the case with proving a statement or proving its negation, when you're proving the statement, you have two things you need to prove. So you need to show it spans and it's linearly independent. Whereas if you want to show the negation, you only need to show one of two things. To show one, that it does not span, or two, that it's linearly dependent. Okay, now let's try and apply that. So let's look at the standard basis for R2. So again, that was 1, 0, that's our E1, and 0, 1 is our E2. Okay, so we saw earlier that this is linearly independent. How do we show that it spans? Well, consider any vector in R2. That can always be written in the form AB, right? So any vector in R2 can be written this way. Well, then once we have it in this form, it's quite easy to see how to cook it up using our basis vectors. You just take AB and reduce it to A times 1, 0, or E1, plus B times 0, 1. Okay, and from there it's easy to see that we have spanned the whole vector space. Okay, so since this set of vectors is linearly independent and it spans, we conclude that it's a basis. Okay, so if the standard base is a basis, why would we want to even use another basis? Why are we looking to prove that things are bases? What use can that have for us? Well, here's an interesting example of a real-world interpretation of R2. Okay, so if you've traveled around at all, you've seen that there are lots of different kinds of showers in the world. And if you go to a particularly old school place, you might see a shower where the controls are basically an R2. So you have two knobs, and one of them controls hot, and one of them controls cold. Okay, so you can move one knob that gives you a component in the hot direction, that scales the hot basis vector. Okay, or you can move the cold knob, and that scales how much cold water is coming out. And people who have tried this kind of shower know that it's a little bit frustrating to use because, let's say you get it to just the right temperature, but not enough water is coming out. So you're going to try to turn up the hot knob and the cold knob, but now it went up in the wrong ratio, and now the temperature is wrong. So you have to try and recalibrate the temperature, but now the intensity is wrong. So it's your basis vectors, even though hot and cold will get you whatever flow you're looking for, hot and cold is not the easiest way for you to think about it. Instead, what you really want is one of these newfangled shower controls on the right. And here we also have two knobs. So it's another version of R2, but the basis vectors here are temperature on the bottom, and on the top it's intensity. Okay? So this is obviously more mechanically complicated to engineer because there's all sorts of computations that need to go into that that control. But for the user, it's much more, these basis vectors are much more relevant. I know exactly how to get the shower to be the way I want it by changing one basis vector or the other. I don't have to play around with both basis vectors at the same time. Okay, so here's a set of vectors in R2. And the first thing I see, so again, to determine whether it's a basis, we need to see if it spans and if it's linearly independent. Okay, so straight up, I see that it's not going to be linearly independent. Why? Because there are too many vectors. This is 3 vectors in R2. Okay, so right away I know it's not a basis. But let's say I forgot about one of these. Okay, so let's say I want to take these 2 vectors. So how about this? Are these linear? Are these a basis? Well, we need to see if it spans and if it's linearly independent. So first up, let's check that it spans. So if we have AB, so let's So we want to see if AB can be written as a sum of C1 times 3, 1 plus C2 times 4, 1. Okay. Well, this is kind of the same thing as the following equation. I'm going to just make a new page here. Okay, here are vectors again. So what we're really looking at here is if we have 3, 1 and 4, 1. Actually, it should be like this, 3, 1 and 4, 1. And we multiply it by the vector C1, C2, will there be a solution for A, B? Okay. And what's cool is that a necessary and sufficient condition for this to be true in general is if this matrix is invertible. So this is a solvable system if the matrix is invertible. Okay. And how do we know when a matrix is invertible? By computing the determinant, which is true if the determinant of 3, 4, 1, 1 is not equal to 0, and in fact, it's equal to -1. So since it's -1, it's invertible, so the system, so the pair of vectors spans. Okay, how about linear independence? Well, here we can actually use the same setup. So if we have 3, 1, 4, 1, C1, C2, we're saying this is equal to 0, 0. If this matrix is invertible, I can multiply the inverse on both sides of the equation. So let's say this is A. So let's multiply A inverse on both sides. Okay. On the left-hand side, these matrices cancel and we get C1, C2. And on the right-hand side, whenever you multiply a matrix by the vector 0, 0, you get the vector 0, 0 back. So we get that C1 is equal to 0 and C2 is equal to 0. Which implies that these are linearly independent. Okay. How about vectors in R3? So we have 3 vectors, 1, -1, 0, 1, 0, -1, and 0, 1, -1. And we want to know if this spans and if it's linearly independent. So we're going to use the trick from last time, from the last computation we did, by setting everything up in terms of matrices. So here we have the idea that C1, 1, -1, 0, plus C2, 1, 0, -1, plus C3, 0, 1, -1, equals 0, 0, 0. This is the same as saying we have a matrix equation, 1, -1, 0, 1, 0, -1, 0, 1, -1, times the vector C1, C2, C3 equals 0, 0, 0. This is for linear independence. And again, this boils down to the existence of this inverse matrix. Okay. Okay, and so we just have to determine if this is an invertible matrix. And as with the 2 by 2 case, a 3 by 3 matrix is invertible if and only if its determinant is non-zero. So let's compute a determinant. Okay, so we can use the cofactor expansion. So we have 1 times this determinant, 1, 0, 1, minus 1, minus 1. And then minus 1 times the, so right now, sorry, I should be more explicit. I'm going along the first row. Okay, so when I take the first term, so I get this times this, that's what I put over here. And then in the next one, I have minus, because you always switch off the sign. And it's this 1 times this submatrix. So it's minus 1, 1, 0, minus 1. Okay, and we can compute this explicitly. So it's 0 times minus 1 times minus 1, which is positive 1. So that's 1 minus, and then this one is minus 1 times minus 1 is 1, minus 0, so that's 1. So we get 0. So the determinant is 0, which means it's not invertible. Okay, so that means not only is this not linearly independent, it also does not span. So it's linearly dependent. So how could we demonstrate an explicit vector of coefficients that make these things add up to 0? Well, we can solve this augmented matrix. Okay, so we would take this matrix and do some row operations. We can take row 1 plus row 2. That gives us 1, 1, 0, 0, 0, 1, 1, 0, 0, minus 1, minus 1, 0. Okay, now we just do row 2 plus row 3. And we get 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay, so what this tells us is C1 plus C2 is equal to 0, and C2 plus C3 is equal to 0. Okay, so that means C3 is free, so we can set C3 to be equal to 1, then C2 is minus 1, and C1 would be 1. Okay, so trying that out, we get 1 minus 1, 0, plus negative 1 times 1, 0, minus 1, plus positive 1 times 0, 1, minus 1, and you know, doing the arithmetic, we get the 0 vector. Okay. Nice. So let's go from there to an example of polynomials in P2. So here we have x squared and x minus 1 squared. Okay, so we need for this to be spanning and for it to be linearly independent. Okay, so here we're looking at, let's multiply this out so it's a bit clearer. So we have x squared minus 2x plus 1, and this is x squared. Okay, so the first thing to observe is that this is certainly linearly independent. Okay, because if we have ax squared plus b x squared minus 2x plus 1 equals 0, well, we know that a plus b is going to have to be equal to 0 because that's the coefficient of x squared. And we have minus 2bx plus b equals 0. So this tells us, first of all, the constant term is b on its own. So that tells me that b equals 0. And then the fact that a is the coefficient of x squared on its own tells me that a is 0. Okay, so that means that this is linearly independent. On the other hand, this doesn't span. Okay, and I'll give you an example of a polynomial that's not in there. Okay, so I'm going to claim that the polynomial 1 is not in the span. Okay, and the reasoning will be very similar. We're going to take ax squared plus bx squared minus 2x plus 1 and set that equal to 1. And immediately we see the constant term on the left-hand side is b, and the right-hand side constant term is 1. So that tells me that b equals 1. But what that leaves me with is let's write it this way, a plus 1 times x squared minus 2x plus 1 equals 1. But on the left-hand side, we have minus 2x as our degree 1 term. And on the right-hand side, we don't have any x terms. Okay? So because the x term on the left-hand side is minus 2x, and on the right-hand side is 0, these two cannot be equal. Okay, and that implies that 1 is not in the span. Okay, so our set is not a basis for P2. Okay. So brief tangent to describe infinite dimensional vector space. So we've been talking about bases for vector spaces. If a vector space has no finite set as a basis, then it is called infinite dimensional. Okay, and here's a quick example of that. So when we write P infinity, we mean the vector space of all polynomials of any degree. Okay, so it's pretty clear to see that if we take 1x, x squared, x cubed, x to the fourth, etc. So this is a set which would serve as a basis for the space of polynomials. This would be a basis for the set of polynomials for p infinity, because it's linearly independent, since you can't combine polynomials or powers of different degrees to get another power, and it spans. But it's not finite. So p infinity, the space of all polynomials, is infinite dimensional. Okay. Now the last topic will be coordinates relative to a basis. So we've been identifying different sets of vectors, just determining whether they are bases or not bases. If we have a basis, we'd like to be able to express a given vector in terms of that basis, okay? And that's what we're doing on this slide. If S is a basis for a vector space V, and V can be expressed as a linear combination C1, V1 plus up to Cn, Vn, then the scalars C1 through Cn are called the coordinates of V relative to the basis S. Okay, and the vector C1 through Cn is called the coordinate vector of V relative to S, and it's denoted Vs equals C1 through Cn. Okay, so with the standard basis, this is exactly what we're used to. So we have our standard basis S equals, let's say we're in R4. So we have E1, E2, E3, E4, which are the vectors given by 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, and 0, 0, 0, 1. Okay, so if this is our standard basis, then any vector we have, so V equals 2, 1, 7, 8. Okay, what this really is saying, this is V sub S, and this is saying this is equal to 2 times E1 plus 1 times E2 plus 7 times E3 plus 8 times E4. Okay, and so that's really what we mean when we write down coordinates of a vector. We're writing it in terms of our standard basis. Okay? But how about in another basis? So let's say we have U1 equals 1, 1, 1, U2 equals 1, minus 1, 0, and U3 equals 0, 1, minus 1. Okay, this is a basis of R3. So let's write coordinates for the vector 1, 2, 3, where that's the expression in the standard basis, relative to the basis U1, U2, U3. Okay, so we want to be able to find C1, C2, and C3 such that this equation is satisfied. C1, U1 plus C2, U2 plus C3, U3 is equal to 1, 2, 3. Okay? So this again is a matrix equation. So we're basically looking at 1, 1, 1, 1 minus 1, 0, 0, 1 minus 1 times C1, C2, C3 equals 1, 2, 3. Okay, and to solve this matrix equation, we can go to the augmented matrix as before. So we have 0, 1, minus 1, and then 1, 2, 3. Okay, so we'll start with minus row 1 plus row 2, minus row 1 plus row 3. And we get 1, 1, 0, 1, 0, minus 2, 1, 1, 0, minus 1, minus 1, 2. Okay, so far so good. I'm going to swap these two rows. So we have 1, 1, 0, 1, 0, minus 1, minus 1, 2, 0, minus 2, 1, 1. Okay, and now I'm going to just multiply this row by minus 1, so we get 1, 1, minus 2, and down here as before. And now I'm going to add minus row 2 to row 1. And I'm going to add 2 row 2 to row 3. Okay, and we get 1, 0, minus 1, 3, 0, 1, 1, minus 2, and 0, 0, 3, minus 3. Okay. Now let's grab that matrix to the next page. Okay. And we want to simplify further, so we can take, let's multiply this by a third. And we get 1, 0, minus 1, 3, 0, 1, 1, minus 2, 0, 0, 1, minus 1. Okay, next up we can add row 3 to row 1, and minus row 3 to row 2. And we obtain 1, 0, 0, 2, 0, 1, 0, minus 1, 0, 0, 1, minus 1. Okay, so this tells us that C1 is equal to 2, C2 is equal to minus 1, and C3 is equal to minus 1. And let's see how that works with our vectors. It's 1, 1, 1, 1 minus 1, 0, and 0, 1, minus 1. Sorry, it's 1 minus 1, 0. 0, 1, minus 1. So we're saying we should be able to take 2 minus, or plus minus 1 times this, plus minus 1 times this, gives us, well, it's in the first coordinate 2 minus 1, so that's 1. In the second coordinate, it's 2 plus 1 minus 1, so that's 2. And in the third coordinate, it's 2 plus 0 plus 1. Or 3. Okay, and so that's the vector that we were looking for. So what we could say here is that 1, 2, 3, if I wanted to take its coordinate vector with respect to s, that would be 2 minus 1 minus 1. Okay? As for this second question, what vector has coordinates 3, 2, 1 relative to the basis u1, u2, u3? What that means is we're looking for v, which is given by 3u1 plus 2u2 plus u3, and that's easy enough to do explicitly. So we take 3 times our u1 plus 2 times our u2 plus 1 times our u1 to obtain 3 plus 2 in the first coordinate, 3 minus 2 plus 1 in the second coordinate, or 2, and 3 minus 1 in the third coordinate, or 2. Okay, and that's the vector that we would be looking for. Okay, so hopefully that gave you a nice flavor for bases and coordinates, and linear independence, and I'll see you next time. Thanks for your attention.